Feel free to interrupt me with questions. It would be a bit weird if I did a reactive presentation and not be reactive. So I've got some possibly confusing mixed examples that I need to warn you about, which I should probably have improved before I started. But essentially, I've got like a generic kind of ABC example and then like a specific audio thing, and they're kind of unrelated. So anyway, if you get confused at all, just let me know. And I'm also not showing any real code. I don't have any real code. All my real code is kind of proprietary, and I can't show any of that stuff. But so it's all kind of pseudocode. So bear with that. And yeah, let's get started. A little bit about me. I've been doing this embedded stuff for about 15 years, something like that. Mostly in the audio industry, specializing in bare metal and real-time stuff. Bare metal, just, no operating system, generally no real-time operating system of any kind, and just low-level stuff mostly. So that's me. So what exactly do I mean by reactive? I'm mostly kind of talking about moving away from a polling model and thinking about embedded architecture in terms of asynchronous and callbacks, that kind of thing. I want to kind of focus on CPU efficiency, CPU time efficiency, power efficiency, and generally only doing work when there's work to do, and knowing when there's work to do, and otherwise not doing any work. And I want to keep things very simple. One of the things that I like about this approach is that it's hopefully quite easy to understand or reason about from the developer's perspective. And I hate complicated things that are too difficult, so I'm trying to optimize for the developer as much as possible. So part one, I'm going to go through kind of the way that we normally do things, and then maybe tip it on its side, and we'll see how that works. We'll look at regular polling architecture, background loop. I've always called it background loop. I've heard it called super loop, stuff like that. I don't know what you folks call it, but I've always... Main loop, yeah. It's same thing. And yeah, I should start by saying there's absolutely nothing wrong with main loop. Most of my projects have been in this scenario. Anyway, so let's look at Arduino. I'm sure most of you are familiar with an Arduino setup. So if you would create like a blank sketch, I think they call them, you'd get something like this, where you have this setup function, which runs once at the start, and then this loop, which is kind of continuous. So you would set everything up in at the start, and then in the loop, that's where all your kind of business logic goes in there, and that runs continuously. So if we were able to step up the stack a little bit, we'd find this stuff that the Arduino system creates for us. So we'd have like an initialization for whatever Arduino stuff, and then this, then we call our setup function, and in our background loop, we call this loop function. So this is our C++ entry point. Here's like the most basic Arduino example, Blinky. We'll set up a pin to whatever pin's attached to an LED, and then turn it on, wait a bit, turn it off, etc. It doesn't get any more simple than this. I'm just showing this to like intro my little timing diagrams. So on the left here, we've got like what the CPU's up to, like what the program's up to, and this LED built-in thing, which I guess that would essentially be what you would see if you plonked a scope on this. So we run the setup function, digital write, LED goes high, wait for a bit, digital write, LED goes low. You get the idea. Let's do something a little bit more complicated. I mentioned my little ABC example. This is that. So these could be, whatever. I mean, let's say you're running a few different tasks, like reading some sensors, reading a bunch of UI from your panel, and then chucking stuff out to a communications port, or running a display, something like that. Our tasks might look something along the lines of this. So you kind of come in and check if there's any work to do, and then if there is, grab grab your data, do your processing on it. You get the idea. Most of the time, we probably come in here and we don't do anything. And then occasionally, this function will take like a really long time. And then we're gonna run task B after this, and task B is gonna kind of have to wait for task A to finish, right? Because we just got the one CPU, and we're just gonna do one thing at a time. This is gonna lead to potentially, like, worst case scenario might be a little bit inconsistent with our timing. Because if we're doing loads of stuff in task A every now and then, task B and C are gonna kind of wait a while task A does that stuff, all right? So let's look at audio example. So I got like an I2S peripheral bringing audio data in. I2S is just kind of like a typical inter-IC sound protocol, which is how you kind of might transport audio data from, say, an ADC into your microcontroller. So a sample will come in, and this is all this I2S peripheral side. This is all implemented in hardware, and our CPU's at the bottom there. So the sample will come in, and it'll get loaded into like a buffer. At this point, we've got this audio data available. This sample's ready for us to read from the CPU, and we get this status flag, which will go high and say, by the way, I've got some audio data here. If we happen to be checking for this flag in our program logic, then we'll see this go high, and we'll read the data. And by reading this buffer, it's going to have this side effect of clearing out the buffer. So now that buffer's ready for the next sample, which is important. And our sample ready flag goes low because we've no longer got any sample in there. So next sample comes in, everyone's happy, and we have no overflow in this scenario because we're always checking this flag. We see the data come in and we grab the data. If we happen to be doing something else at the time, when this sample comes in and sample ready goes high, and we don't notice, then what happens when the next sample comes in is, well, it's just going to get written over the top of the first sample. We've just lost that data completely, and we'll see this overflow flag go high to let us know that we've had this error. But we're not probably not really going to do that. We're not just going to be sitting there checking for this flag. We're going to use the interrupt system. So let's look at the same example, but with the interrupts. So our sample comes in, and when this sample ready flag goes high, we get like an event notification, right? So we get this interrupt. So we pause whatever we're doing, and we'll run this I2S interrupt. In there, we'll do our sample read. We'll collect our data, and then we'll go back to whatever we were doing, and so on. Any questions so far? All good? Like typical interrupt might look something like this. So we'd enable this in hardware. So at some point, the hardware is going to come along, and this event's going to happen, and it's going to just basically tell our CPU to execute this function at a particular memory address. And we just happen to have this function sitting at that memory address. So this comes in from our CPU event, and our linker is going to hopefully put this function in the right spot. So we execute this. We'll check our status flags. We'll grab that from the hardware. If we happen to be responding to our buffer's not empty anymore flag, so we've got our data coming in, we might just push that onto like a FIFO or something like this, something real quick. And we'll also need to respond to our error events and maybe clear our status flags. We might not need to clear the status flags. That is very much implementation defined. They might just get cleared when we read them. So our receiver task is kind of just checking, rather than checking the hardware directly, we're just checking that FIFO because that FIFO is being filled from the interrupt. So this also has that kind of inconsistent timing kind of situation where, because like pretty much most of the time when we're running this function, we're not doing anything because there's nothing to do, but every now and then. But it doesn't matter anymore because all our real-time stuff is being handled by interrupts. An interrupt looks kind of something like this. We'll get like a trigger of some kind, and then the CPU will pause whatever it's doing, stash its working registers, execute whatever this memory address is, and then go back to whatever it was doing when you return. So we get to the next part, scheduler, because we're probably not gonna actually just sit in our loop just running these tasks. We might wanna kind of say, well, I only need to run task A every now and then, task B, some other frequency, for example. We might say, well, I'll run my task A, maybe it's like a sensor, so I'll run that every millisecond, that should be quick enough. And we'll check for data in there. And maybe I'll run my UI at 10 milliseconds, that should be quick enough for button presses and things like that. And 25 hertz for my little display or whatever display I've got on my little micro. These are just kind of examples. So we might initialize our scheduler with some kind of like time base, some kind of minimal, this is our granularity. We're gonna check for events and tasks every millisecond. And then we'll add our different, we'll just chuck some function pointers in. And in our background loop, we just run our scheduler. And let's see, our scheduler initialization, we're gonna grab a timer, initialize our timer to whatever our time base is gonna be, and tell it to interrupt whenever this timer event occurs. Our add function is gonna be something like, we pass in our time and our little pointer function, we just add that to like a list of events that are gonna run. And our timer interrupt, which is where, you know, most of this is the important part. We're gonna read our status, and this, I think they usually call it like update or something, or where, you know, we get to our time and then it kind of resets and we get this interrupt. We're gonna go in here and we're gonna go through our events list and just update some counters. Keep it short and sweet. And then in our run, which is being called from the background loop, we'll grab our events list and we're just gonna run some calculations on our counters. And we're gonna see, well, has enough time passed since we last ran for each task? And if it has, we'll run the task. So this is gonna look something along the lines of this. Every millisecond, we're gonna run, well, the first millisecond, we run everything. You might not set up your scheduler like that. You might kind of have everything wait until the second event. So maybe task C doesn't run yet. So next millisecond, just task A, 10 milliseconds go by. We've got A and B. And then after 40 milliseconds, all three of them are gonna run again. So this is just a naive implementation. You might stagger this somehow. So you might say task C and B never run on the same millisecond point. But I'm just keeping it simple for the time being. All right, so there is a nice little flaw with this particular scheduler. Any ideas like how we might break this thing just with our regular development as day by day goes by, and one day we make a change and suddenly this breaks. Any ideas? No? Okay. Yeah.
If task C takes too long, then you're next. Like task A can be out of sync where it's supposed to be.
Right. Yeah. Cool. That's kind of what I was going for. Yeah. So brief tangent. I worked on like a little proof of concept kind of prototype, which was based on a legacy product. The idea was to basically take this product that's already out there and just kind of make it bigger and faster, etc. What could possibly go wrong with that? So everything was fine, except that it was kind of a bit buggy, a bit unstable, unpredictable. And it took a really long time to figure out what was going wrong. We kind of took this thing and it had like a higher resolution display, you know, all this kind of stuff. And it just turns out that one of our tasks was just taking a really long time, pretty much exactly how you said. And the problem with this is that, yeah, while this task C is executing however long it takes, I can't run task A or B. They have to wait until task C is done, because I've only got the one CPU and it's doing all the work. So it's, you know, everything's still kind of working, but the timing's all off. There's a bunch of potential solutions to this problem. I'm sure you can think of more. We could make all our buffers for our I/O really, really large. So like, for example, our FIFO from earlier could just be really, really big. So it doesn't matter if everything's waiting for tens of milliseconds because we've just got enough space to put everything in. This turned out to be a really bad solution because it really pushed the latency into a place where stuff was just taking too long. Maybe not even latency is the right word, but changes in the latency, because every 40 milliseconds I suddenly had no response. I could have potentially split this long function up, like maybe we take like a state machine and just chop it up into bits and then run each bit whenever we can. That's a pretty good solution, as long as you know the code. The problem I had with it is that I didn't write this really big chunk of code, and I had very little confidence that I would be able to learn and understand it quickly enough to understand it well enough to chop it up and then still expect it to work. And it also introduced a level of complexity to that part of the system that I didn't fancy. I could use a real-time operating system. That's actually a pretty good solution in most scenarios, because you could just kind of schedule this stuff with a proper scheduler, right? I didn't do that because I didn't feel like I had the memory space for a real-time operating system. So you might find that your microcontroller you just can't afford to put a real-time OS on there, which would be a real shame because that's a much easier solution. But yeah, so what do I really want to happen here? Really, I just want to kind of pause task C and let task A run, right? Because, and the same for B. I just want to kind of maybe let task C take however long it needs to do, but just pause and let everything else happen. This is starting to look a little bit like the interrupt from earlier. So maybe we'll just add to our scheduler this little kind of extra flag for certain tasks, right? We'll tell them, run at a higher priority. And task C, leave it where it was. And this time around, we'll come around and we'll iterate through our events and say, well, actually, in our little timer interrupt, we'll just think, just for the high priority tasks, we'll kind of check whether they need to run right now. And we'll run them right now in interrupt context. So they will interrupt task C. The problem is, of course, the interrupts are supposed to be kind of like short and sweet, right? You don't want to be spending a lot of time in your interrupt, and we're potentially going to be spending a lot of time in our interrupts. And normally you just go into an interrupt, set a flag, and then exit, like quick as you can. Come and just get out of there. Because, but if we have preemptive interrupts, then we potentially have an interrupt system which can interrupt itself, right? So we might be able to just say, well, well, you've got a set priority, you can interrupt, and you can be interrupted by this other interrupt, which has got a higher priority. That could work, right? So what does that look like? That kind of looks like, so I got our priorities on the left, low and high, and if we have our low priority task, we might interrupt it with a slightly higher one, etc. You get the idea, and when they're done, we all go back down. This is starting to look probably a bit like a threading system, which it sort of is. If they all occur at the same time, then we'll just kind of run the most important one and then cascade back down. This is very much how the ARM NVIC interrupt controller works, the nested vector interrupt controller that's in most ARM chips, most ARM microcontrollers. So you've probably got this feature. You might not, but you probably have. In which case, our interrupt-based scheduler kind of looks like this now. We've got our task C taking just as long as it likes, and everything else is more important. So we're interrupting it. We're achieving this by running A and B in interrupt context. So the problem, of course, with this is that we still have our hardware interrupts, right? So we still have, like, for example, that I2S interrupt, which is more important still. So we really have to kind of think about how we might split our hardware and software triggered interrupt priorities. So we might have, say, some kind of split somewhere. So if you're going to do something like this, you got to make sure that your hardware interrupts have always got precedence over any kind of sort of, I'm calling them software interrupts because we're scheduling them from software, and they're not being triggered by any kind of hardware event. We're triggering them ourselves from our little scheduler.
It might be slightly silly, but when you pause a task halfway because it gets interrupted by something else, do you ever end up in states that are slightly unknown because variables are being used by other tasks that haven't been finished?
Yeah, if you're in the middle of something and you get interrupted, you're going to have your CPU registers right in the middle of whatever calculation they're doing, right? And what happens is that stuff is going to get stashed, and then the CPU registers would then fill with whatever your interrupt task is doing, and when that returns, that stuff gets kind of popped back in, and you carry on as if nothing happened, if everything goes well. So if you're sharing data between these two, then you could have an issue. So you're going to have to kind of think about synchronization to an extent, but that should be okay. Does that answer your question?
So my question is about the interrupt handlers. So are you telling us that an interrupt handler can be interrupted by another interrupt? Okay, I wasn't aware of that. Thank you.
Interrupt system would essentially say, I've got this low priority low priority function. If a higher priority function comes along, I'm going to interrupt that as if it was just in the main loop, right? Carry on. For however many levels you've got, which might not be too many actually. If you're running like an STM G0, you might only have 4 interrupt levels.
Yeah, because you need to stack those registers.
Yeah. Yeah, but of course you could have like 2 interrupts that are the same priority, but they're just not going to interrupt each other. They're just kind of whichever one's running right now will finish before the next one runs. And if they both occur at the same time, see your local data sheet for that. Yeah, and of course not all interrupt controllers are the same. So for sure, check this stuff if you're going to try this out. Yeah, so where do we go from here? We're almost running our whole system in interrupts. So where do we go? What's next? Well, I will go back to our I2S audio example. I'm going to kind of rearrange this a little bit because I would never really do this. This is a bit of a ridiculous thing to do, to kind of look at every sample individual. I don't really care about every sample. I would care more about like a buffer of samples. So I'm going to grab the DMA and get the DMA to service this interrupt for me. And so the DMA is direct memory access. So this is essentially another peripheral which will give our I2S peripheral direct access to the RAM. So the I2S effectively can write its data straight into the RAM, which is really handy because it means that I can just kind of leave that to run, and when we've got a whole buffer of data ready, I'll get this interrupt instead. So here I'm getting this interrupt whenever this buffer is full, and in my interrupt I'm going to say to the DMA, okay, I want to do some processing on this buffer, so you go fill a different buffer now, and while I do this work. So we'll swap this buffer around, and then rather than waiting for our little 1 millisecond task or something like that, I want to process this right now. So I'm going to trigger a soft interrupt to run right now because I know that I've got work to do and I want to process my audio buffer. So I'm just going to schedule that right now, and I'm going to call this a pseudo coroutine because it's not really a coroutine, but it's kind of a coroutine, and that's kind of how I'm using it at this point. So rather than having like this scheduler time run this process in some sort of timed manner, because I know exactly when this data is coming in, I'm going to just do it right now. So my DMA interrupt handler might look something like this. We'll kind of check whether the buffer full event has occurred. And if it has, we'll quickly swap the DMA buffer and re-enable it. You might not actually need to do this. Some DMA controllers will have this feature built in, so that part might be automatic. And our scheduler now only has this one function, which is schedule this lambda to happen, whenever you can. And this is going to schedule it as a little. I've got this high priority scheduler priority level, and this is going to run in interrupt context, but it's a lower priority level. This is important. It's like a lower priority level than the actual DMA interrupt. So this won't execute right now. This will be pending right now, but it won't execute until we exit this function. So as soon as we exit this function, we're going to be calling this execute, and this is going to, this is a little bit confusing because I'm using a timer here. This is just kind of, I'm using a timer as my sort of entry point into the interrupt system. So I'm going to grab a timer, and I'm going to put my function into my little timer class. This is the lambda that I want to run. And I'll enable this interrupt for the timer at whatever priority level, which will be kind of like a mapped priority level, right? So I've got my scheduler's got its priority levels, but my real priority levels are like much bigger, right? So we're just sort of the highest software priority level. So this will get mapped to that, and then I'll just tell my timer, just interrupt now. I'm not really using the timer as a timer. I'm just telling it, I'm just using it as like a really simple way to execute an interrupt. So my actual coroutine is going to be whatever timer. So let's say, for example, the timer I got was timer 14. I'm coming into timer 14, and I'm checking whether we're in this kind of process and whether I've got a function to run. And if I have a function to run, we'll execute the function and then return the timer back to the list. It looks a little bit something like this. So here we got our priority levels. So here I've kind of got a split of 2 hardware level priority levels at the top, and then some software priority levels. So task C gets interrupted by some sort of hardware event, which could be like our DMA interrupt. That schedules task A to run, which is going to be like our whatever processing. We're going to process whatever data came in that hardware interrupt. So another hardware interrupt occurs, so that's going to interrupt task A, because it's a higher priority than task A. But B is going to schedule task B, right? Because we've got data for task B. But task B is not going to run just yet, because task B is a lower priority than task A. And by the end of this, we're looking very much like a threading model. We're using our interrupt controller as kind of like a hardware threading system scheduler kind of thing. So our main task is going to go from looking like this to looking a bit more like set everything up and then go to sleep. So in our background loop now, we're just calling this wait for interrupt thing. So this is just an ARM instruction which kind of says puts the CPU into like a low power mode, puts it to sleep basically, and wait for interrupts. So as soon as there's any interrupt, we'll wake up, execute that interrupt, and then we'll iterate the background loop again and go to sleep. If we were being, this is quite an important part of it because you might use this background loop now to do kind of basic benchmarking. You might say, put a counter in there and you'd be able to know how much time your system is idle. So you might say, well, I'm spending a lot of time idle. Maybe I can use a slower processor. Maybe I can get away with that. Or I'm using way too much time. I need a faster one. We could also, you don't need to read all this. This is just an extract from a data sheet. So this particular controller's got a sleep on exit bit in its controller. So we can just say, well, I don't even need a background loop anymore. I can just put my CPU to sleep and execute the entire program in interrupts. That might be a little bit silly, but something you could do. Just wrapping up now. Are there any questions at this point? So why might you do this? So the idea here is that you can potentially make your timing very easy to understand because everything is kind of happening in this prioritized kind of stack. So let's say you've got a part of your system that's really, really important, you just make it so it can't be interrupted by any other part of your system. So it's always going to be at the top, always the most important thing, apart from maybe hardware events. It's pretty lightweight, it's much smaller. You'll end up having a much smaller code base than if you would use a real-time operating system, which do most of the same things. It's also just kind of an interesting thing to try. I was dying to try this thing ever since I saw a talk about a system called Correct, C-R-E-C-T, which is a reactive thing, very much built on terrifying template metaprogramming code. I didn't show any template metaprogramming code because I rarely use that stuff because I don't understand it. But it's an interesting alternative, and I've been wanting to try that stuff ever since I saw that. Yeah, I mentioned the Nordic soft device. I'm pretty sure they, over at Nordic, do something very similar to this, because if you grab one of the NRF chips and you run their soft device on it, you've effectively got a single core processor that's running this other program while your programming is running, and it's probably doing everything in interrupts. I don't know that for sure, it's closed source, but it's probably doing this kind of stuff. And one of the reasons the Correct guys were using this kind of system is basically for reliability. They were making like a drone, and they were kind of sick of their drone falling out of the sky. So they kind of prioritized the flying part of their system, and it to great effect. I've also got some of this. Obviously, I haven't shown any production code, but this is my go-to when I'm doing bare metal stuff these days, because it just it ends up being very easy to reason about the timing and the structure of the system, right? So if I've got a problem where I've got a task which is it needs to be elevated in some way, then I can do that, right? But I know that if I elevate this task, then it's going to interrupt another one, and you could probably sit there if you're a mathematician and work out exact timing for the whole thing, because the timing is guaranteed by the interrupt controller hardware. And if you trust your hardware, then you can trust your scheduler, because your scheduler is a hardware scheduler. There are some caveats, of course. Your scheduler has to be preemptive, so it has to have the capability. Not all of them do. We've got to be able to interrupt our interrupts with another interrupt, with a higher priority and we've got, in this particular example, I'm showing every task has got to have its own timer. You might not have that many timers. So the last microcontroller I used had something like 17 timers. So it's kind of not that big a deal. But this isn't the only way to do this stuff. So the Correct guys used kind of like a gap in the interrupt vector table. If you don't know what I'm talking about, then I've maybe got some slides at the end. But essentially, you've got this interrupt vector table where if you have an interrupt, it'll have a number, and that number's going to index this table, and the table is just kind of a list of your interrupt handler functions, right? But there are gaps in that list, in that table, and you can put your stuff in those gaps, and maybe, fingers crossed, internally that's hooked up, so you can call that. That's what they were doing anyway. So I'm just showing timer as like a way into the interrupt system that's kind of easy to use and understand, but there are other ways to do this. There's also PendSV, which is kind of like just a user interrupt, but that would have, well, I mean, that's kind of what RTOSs will use. We'll use PendSV, so you could look that up. Security, yeah, you probably want to think about security, because if you're running the entire system in interrupt level, then depending on whether you care about this stuff, you're essentially running your entire system with elevated privileges. Some microcontrollers will allow you to do stuff in interrupt, which you can't do in outside of the interrupt system. So you potentially have an issue there where something malicious could come in and do something that you might not, which might be normally protected. Timing, yeah. Yeah, okay, I realize how I've confused myself here. Basically, what I'm meaning to say is that there are harsher consequences for making mistakes in your timing, right? What happens if your one of your interrupts now kind of overflows its time, right? So let's say my audio buffer comes in, I schedule my process, and my process now takes so long that my next audio buffer is ready. Now what happens, right? I mean, that's a typical real-time problem anyway, but you're going to have pretty harsh consequences for that happening. So you're going to want to think about that. You also want to think about synchronizing. If you're sharing any data between your interrupts or between your interrupt and the background loop, then you need to think about synchronization. I should also mention Cortex M0 and ARM v6M. This doesn't have, they don't have exclusive load and store instructions. So if you were just using stood atomic, you wouldn't be lock-free. And that's kind of important. And you also need to kind of check that if you are locking, that you're doing the right thing when you're locking. And when I say locking on a single CPU microcontroller, a lock basically means switching off interrupts for the amount of time that you're locking. You got to make sure that whatever code the compiler's outputting is doing the right thing. Check out the EMBO correct talk, which is goes into sort of detail about this kind of thing as well. This is kind of what inspired me to try this stuff. It's a great talk, and I always refer to Fabian and Dave's Real-Time 101 for synchronization, stuff like that. It's a great talk. And look into PendSV as well. Thanks very much for listening.
I'll just ask this one quickly. You mentioned just a few minutes ago that if your process function takes too long, then you kind of mess up your timing. Are interrupts recursive? So could your interrupt itself, but just with a different stack to try and process a buffer, and then if that completes quickly, then it goes back to trying to process another buffer? Like, can you get weird interleaving like that, or will it just not do it?
Typically, what's going to happen if you reschedule your interrupt is that you'll re-enter your interrupt once you're done. You'll kind of wait. You won't interrupt yourself.
Okay.
What will happen is you'll be pending from that point, and then you'll rerun yourself. I mean, that example, if I couldn't process my audio buffer in time, what I would basically say is buffer that buffer, right? Give yourself a little bit more room for that. I mean, it's the same problem you'd have in any kind of audio system, right? You've got to do your work before the next set of data comes in.
Yeah, so you're just like overflows, not like
you'll have this. Yeah, I mean, again, you'll have this weird situation with the DMA, because the DMA can't touch a buffer that you can't touch the same buffer that the DMA is touching, right? Because, you'll probably just crash. Hopefully you'll just crash in a nice way. But typically you don't want to be touching the same buffer that the DMA is touching. So if you think you're going to be in that situation, then just like queue that stuff up and then go through the queue rather than interacting directly with the DMA's buffer. Does that make sense?
Kind of.
My question is about tracing all this stuff. Do you have ways of looking at what's actually happening, what interrupts are running at any given time? Like, can you scope this, log this over long periods of time?
Yeah, you could do all that stuff. I mean, the same as any embedded system, really. You'd be at a kind of breakpoint in there, or set a pin or something when you enter all this kind of stuff. You could put some logging in there. There's no reason you couldn't do that. It's really just running. It might be kind of elevated privileges in these interrupts, but it's the same as just running in the background loop, basically. So you could just put some logging in there. Just bearing in mind that adds a bit of time.
I'm a little bit puzzled because I'm an old man. But it sounds to me that this technique where you've got hierarchies of interrupts and everything runs in IRQ mode, you're basically going from a situation where you're having to think really, really hard about time management and race conditions to a situation where you have to think really hard about time management and race conditions. So the slightly cynical question is, what does this get you that the old approach doesn't?
I think it gets you a situation where your timing is easier to reason about. That's one of the main things. And you can kind of say, well, I've got one part of my system which just really can't fail, and I'm going to put that at the top. And other parts of my system can fail, take longer, or whatever. But this bit really mustn't fail.
It's learning to love that priority queue.
Yeah.
Okay.
Yeah. And you know, there's caveats to this stuff, obviously, like anything. At some point, you might just have to get a faster processor.
Suppose I better embrace it and see if I win. Thank you.
Yeah. See if you win. Yeah.
I guess sort of following on from that question, I'm wondering what's your strategy for testing that? I mean, I guess the security thing, you want your bit that's never going to fail. Well, I might observe something and decide to keep that top level thread really busy so those lower ones never get a chance to execute, which might gain me some attack surface.
You probably don't want to do that. Yeah. No, absolutely. It's the same as really any embedded system. You just have to be, you're caring about all the same stuff. It's all real time. You really care about the timing for this. Like you can't overflow your input buffers and you can't starve your output buffers. And you've still got all these constraints. What this is kind of going to give you is maybe a better in your head visual on this timing, and maybe a simple way to kind of rearrange things if you need to. So if you've got a process that takes a really long time, it's very high priority, you might have to make a hard choice about bringing that down and letting some of the other processes take control. Or again, going in and using the same old techniques to kind of split it up. Does that answer your question?